Welcome, my name is Stefan Rodell. I want to present to you our technology of an ultrasonic trap for small particles for them to be measured better. It is an industrial measurement application where we use an ultrasonic field to catch small particles and present them to a sensor. This technology is available for a range of sensors, most of them optical, could be for instance Raman spectroscopy or infrared spectroscopy as well, process microscopy, or we had successful tests with FBRM, focused beam reflectance measurement. Now particles in this context can be cells or crystals or dirt or other even oil droplets, wherever you have an interface to the surrounding liquid. So this defines different fields of application if you think of a crystallization process or biotechnology production, or as well wastewater treatment, wastewater monitoring together with lubricant liquids are in the range. Cells in this context could be biological cells, crystals forming, oil droplets, dirt, and other things to be monitored in, for instance, wastewater plants, or as well production water monitoring, or as well crystallization processes or biotechnology processes. The forces come from an ultrasonic standing wave field. They are exerted on particles and they get a grip on the particle at the interface. The range of sizes start at about 1 micron and goes up to 120 microns. The origin of the forces is the difference or ratio of speed of sound between the particle and the liquid, as well as the mass density. A very important guiding parameter is as well the size of the particle. Now, inline real-time measurements are like this manometer, which is delivering the pressure of the tube behind right now, right at the side. It is not always possible to take inline real-time measurements. Sometimes you have to take samples, carry them to the laboratory, make a protocol, take measurements, and you have a time gap between your process, which is of course developing during this measurement, and the knowledge what was going on in there. And our soniccatch improves this situation in enabling or improving the application of PAT probes within the process. Now here you see our prototype soniccatch number 1, built of FDA compatible materials like 316L steel, 3D printed, Markor, and the construction as well as FDA compatible. The probe would be held in the middle, and the white part down here is the emitter of the sound. We work on the stability, on the sensitivity, and on the specificity of the signal. Now what I mean by that, you see in those pictures, on the left hand side you see particles evenly distributed in a volume. What you see is a whitish, grayish distribution. If we switch on the sound orders the particles in the so-called nodal planes, the pressure nodal planes in this case, and you see in between the clear liquid. So now if you point an instrument on those agglomerates, you will see an increase of particle material. If you look between those planes, then the signal comes mainly from the liquid. And in this way you can distinguish between signal from liquid and particles in line. Now in this example we look into the direction of the sound propagation. On the left hand side, this is not a bad picture, it is particles and most of them are not in focus. Of course when we switch on the sound, then all those particles come to a position which was clear before, so the instrument is focused there and you see all those crystals forming at the same time. You can observe them, you can keep them, you can observe them over time. And the right hand side picture is from the side, and what you see is the particle agglomerations between this 90 mm Raman spectroscopy probe and the ultrasonic transducer. Now the improvement becomes clear when you look at those measurements. These are Raman spectra of theophylline crystals forming. On the left hand side, the spectrum is taken from freely dispersed particles. On the right hand side, the spectrum was taken from an agglomerate of crystals, and you see instantly a very much higher, crisper, more distinct signal, which is easier to interpret. We have compared these signals to other signals, it resembles about the signal of a sediment. The application of ultrasound with the ATR, infrared spectroscopy, is an application that plays around with frequency. In this case, the particles are kept about half a wavelength from the ATR. Now, when we change the frequency, particles are pushed closer and closer to the ATR until they populate the evanescent field. Now, if you think of the information-rich mid-IR, the fingerprint regions, you can take measurements of cells in line, real time, in this case, the yeast cells in the process. Now, what we mean by increasing the stability is shown here. This is the signal of the fouling index of a focus beam reflectance measurement probe, meaning how clean is the window. And as you see with the sound, we can clean the window within minutes. I hope you enjoyed the presentation. Contact us anytime by email or phone.